We're surrounded by machine learning models these days, right? They're quietly powering everything from our photo apps to, really sophisticated medical diagnostics.
Absolutely everywhere.
But have you ever stopped to think about the data these models were trained on, especially when it involves sensitive personal details?
That's a critical point.
Okay, let's unpack this. We've
Hmm.
got some fascinating research here that dives into a really key question. How well protected is that private information, the stuff used to train these AI systems, even after the training's done?
That is the central puzzle we're tackling today. You see, while a trained model is, well, essentially frozen, its learning phase is over,
Right.
right? But there's this field called model inversion, or MI, and it's revealing some surprising ways that attackers might still be able to pull out sensitive information.
Model inversion MI. Okay. It's almost like trying to figure out, say, an original painting just by looking at a really high quality print. So how do researchers even start doing that?
Well, the core idea is using the target model, the finished machine learning model, essentially as a guide
A guide for what?
to train another model. Often it's a type called a GAN, that's a generative adversarial network.
Ah, GANs, right.
And this generator model, it tries to create synthetic data that can basically trick the frozen target model into making really confident predictions.
Okay.
So by sort of iteratively refining this synthetic data based on how the target model responds, the generator can potentially reconstruct something that looks, well, alarmingly like the original training data.
Wow. And here's where it gets really interesting, because if these MI attacks actually work, we're not just talking about like theoretical weaknesses.
No, not at all.
We could see actual training samples being revealed, and that would be a huge privacy breach for anyone whose PII, their personally identifiable information, was used to build the model. Think about medical images or even face recognition data sets.
Precisely. Early research already showed this was possible. They could infer things like genetic markers or even create recognizable faces, though often a bit blurry from simpler models.
Okay, so it's not brand new, but it's evolving.
Right. And more recent work using GANs, sometimes with the help of similar publicly available data sets, we call those auxiliary data sets, has led to even more realistic reconstructions.
But wait, it sounds like a lot of these more successful attacks, they have a catch, right? They often need access to this similar external data or maybe even partial glimpses of the original training images.
That's often true, yeah.
So what happens if an attacker doesn't have those advantages? They just have the model itself. Is it still possible to get at that private training data?
That's actually a significant open research question. And that leads us right into the main topic for today's deep dive, ensemble inversion.
Ensemble inversion.
Okay, so instead of focusing all their effort on cracking just one model, what if an attacker targets multiple related models at the same time?
Ah, like a team effort for the attacker.
Kind of. The thinking is that even if these models were all trained on the same sensitive data, they might have learned slightly different things, maybe focused on different aspects or features.
So it's like having multiple detectives investigating the same case. Each one might notice different clues.
Exactly.
And by putting their findings together, you get a much clearer picture of what actually happened.
That's the fundamental idea behind ensemble inversion. Now, it's important we clarify what we mean by ensemble here.
Right.
We're not necessarily talking about models that were specifically designed, built to work together for better predictions, like a traditional machine learning ensemble.
Okay, so not like a voting system for models.
No. Instead, we're considering a collection of related models. Models an attacker might realistically be able to find or collect from various sources.
Like where? Where might an attacker find a bunch of related models?
Well, think about different versions of software that get released over time.
Ah, like app updates.
Exactly. Each update might have a slightly tweaked ML model, maybe trained on more recent data, or consider federated learning.
Where different devices or organizations train a model together without sharing raw data.
Right. In that scenario, each participant might end up with slightly different local versions or different model updates that could be collected. Even different products from the same company might use models trained on overlapping user data.
Okay, so the attacker somehow gathers this collection of related models. What's the big advantage of attacking them all at once instead of just picking, say, the newest one or the one that seems weakest?
It really comes down to something we call model diversity.
Model diversity.
Yeah. Because of the randomness inherent in how deep learning models are trained.
Yeah.
Things like the initial random settings, the order the data is shown.
So stochastic gradient descent and all that.
Exactly. Different models trained on the exact same data can end up highlighting slightly different features. It's quite fascinating. The research we're looking at even has this great visual, figure 2, showing heat maps from different face recognition models looking at the same faces.
Heat maps showing where the model is looking.
Precisely. And you can clearly see how each model is paying attention to slightly different areas of the face. One might focus more on the eyes, another on the mouth shape.
Huh. It's like each model has its own unique perspective on the data.
You got it.
So, by looking through multiple of these slightly different perspectives, you can piece together a more complete understanding of what the original data looked like.
Exactly right. The ensemble inversion approach really leverages this. The attacker still uses a generator model, like in basic MI.
The GM is what I talked about.
Right. But now, its efforts are guided by the predictions of all the models in the ensemble, not just one.
Okay.
The generator tries to create synthetic data that makes all of these models confidently categorize it in the same way.
And this extra pressure having to fool multiple models at once, that makes the reconstruction of the original training data, what, better, more accurate.
That's the core hypothesis, and the results seem to bear it out. To make this work effectively, the researchers developed some pretty clever techniques, including specific loss functions to steer the generator.
Loss functions, like the error signals used during training.
Exactly. One is called the one-hot loss, or LOH. You can think of LOH as kind of like a sharpening tool for the images the generator creates.
Sharpening. How so?
It encourages the generator to produce samples that make each model in the ensemble give a very focused, confident prediction for just one single class, instead of, a fuzzy guess spread across multiple possibilities.
Ah, okay. So it pushes the generator towards creating clearer, more distinct examples that get a strong, unambiguous, yes, it's this class response from every model.
Precisely. Then the second key loss function is the maximum response loss, or LMR.
LMR. Okay.
Think of LMR maybe as an amplifier. It makes the model really shout its confidence about that chosen category. It pushes the generator to maximize the strongest activation in the output layer of each model.
So the highest score among the possible classes.
Right. A high activation there signals a very high level of certainty in the model's prediction.
Okay, so the generator isn't just trying to get the right classification, it's trying to make all the models in the ensemble feel incredibly sure about that classification.
Correct. These two losses, LOH and LMR, are then combined with other standard techniques used in training GANs, like a loss that just encourages the generated images to be classified correctly by the target models.
Makes sense.
And sometimes another loss, an adversarial loss, that helps make the generated samples look more realistic, particularly if the attacker happens to have access to some external similar data, that auxiliary data we mentioned.
Right.
But what's really interesting is that for the data-free scenarios, where the attacker has no external data.
Which seems like the harder, maybe more common case?
Arguably, yes. In those cases, this realism-focused loss is often not even needed or used. The LOH and LMR seem to do a lot of the heavy lifting in extracting class-specific features.
Interesting. Now, what if an attacker, say, finds dozens, maybe hundreds of potentially relevant models? Trying to attack all of them with this ensemble method sounds like it would need massive computing power.
Absolutely, that's a practical challenge.
Is there a way to strategically pick which models to include in the ensemble? Get the most bang for your buck?
Yes, and that's where a technique called farthest model sampling, or FMS, comes into play.
Farthest model sampling. Okay.
The idea is basically to select a diverse, representative subset of models from a larger pool you might have collected.
How does it do that? How do you measure model diversity?
Well, first, each model is turned into a kind of high-dimensional signature or representation. This is based on how it reacts, how it classifies a whole bunch of random input data.
Okay, so you see how each model behaves on random noise.
Essentially, yes. Then, they use a method called farthest point sampling, looking at the L2 distance between these model representations.
L2 distance. That's like a standard way to measure how far apart points are in space, right?
Exactly. It's a mathematical way of measuring how different those model perspectives or prediction patterns are. So FMS uses this to pick models that offer the most varied viewpoints on the data.
So instead of just randomly picking, say, 5 models out of 100, FMS tries to select the 5 that are the most different from each other in how they see things.
That's the goal. And the research actually shows FMS generally works better than just random selection, especially when you're dealing with a larger number of potential models.
That makes intuitive sense. More diverse inputs lead to a better reconstruction.
Exactly. The more diverse the models in the ensemble, the more comprehensive the information that can potentially be pieced together through this ensemble inversion attack.
Okay, but hang on, there's another potential hurdle for the attacker, right? If they're grabbing models from different software versions or different companies, maybe,
Mhm.
the way the output categories are labeled might not be consistent. Like, one face recognition model might call me ID1, but another, trained on slightly different data, might call me Subject 7. How do they figure out that ID1 and Subject 7 are actually the same person?
That's a critical challenge, absolutely. Class correspondence. The researchers looked into this.
How do they solve it?
Well, one possibility is if the attacker has access to other related info, maybe from social media, other databases, linking usernames or profiles.
Okay, using external context.
Right. But even if they only have the machine learning models themselves, it turns out it's possible to get a pretty good idea of how the categories align
Just from the models. How?
by analyzing how the models respond to the same set of inputs. You feed the same images or data points into different models and look at the covariances of their prediction patterns.
Covariance, like how strongly the predictions for different classes move together.
Exactly. You can identify which category, say, in Model A tends to get activated similarly to which category in Model B when they're shown the same thing. Figure 3 in the paper illustrates this. It's like finding hidden correlations.
So you're looking for patterns in how the different models react to the same stimuli to figure out who or what they're talking about, even if they use different internal labels.
Precisely. It's clever.
Okay, this all sounds quite powerful in theory. Did the researchers actually test how well this ensemble inversion approach works in practice?
They did. They ran a series of experiments using both handwritten digit data sets and also face recognition data sets.
Let's start with the digits. MNIST, I assume.
Yes, the classic MNEST handwritten digit data set. They trained groups of 1, 2, and 4-digit recognizing models. These were the models under attack, or MUAs.
Okay.
And they tested two main scenarios. One was data-free. The attacker had no external data at all.
Right, the tough case.
And the other scenario used the MNIST letters data set as that similar auxiliary data we talked about earlier.
Okay, digits versus letters. Close enough to potentially help, but not the same. And how did they measure success? How good was the attack?
Good question. To evaluate how well the attack worked, they trained a completely separate independent evaluation model, a ResNet 18 classifier on the real MNEST-DS test images.
Okay, a judge model.
Exactly. After performing ensemble inversion and generating these reconstructed digit images, they fed those generated images to this independent judge classifier.
Ah, I see.
The higher the accuracy of this judge classifier on the reconstructed images, the more information about the original training data, specifically the digit labels and appearance, had been successfully extracted. They call this attack accuracy.
Makes sense. So what were the main findings from these digit experiments? Did ensemble inversion help?
Several key results emerged, yeah. They're summarized nicely in Table 1 of the paper. First, as you might expect, having access to that auxiliary MNIST dataset generally led to better attack accuracy.
Okay, external data helps. No huge surprise there.
Right. But second, and this is crucial for their main claim, increasing the number of models in the ensemble, going from 1 MUA to 2 or to 4, often significantly improved how well they could reconstruct the original digits, both in terms of attack accuracy and visual quality.
So more models in the ensemble means a better attack.
Generally, yes. Third, those special loss functions we discussed, the LOH, one-hot loss, and LMR, maximum response loss, they help further boost the performance in most cases. They really sharpen the attack.
Sharpening and amplifying tools.
Exactly. And lastly, they found that filtering the generated samples helped too. If they only kept the reconstructed digits that all the models in the ensemble classify with high confidence, the overall quality and attack accuracy improved. You can actually see this in the visual comparisons in Figure 4. The filtered images look much cleaner.
Okay, that's quite convincing for the digits. Did they also look at that model diversity idea more directly? Like, does having more different models help more?
They did. They looked specifically at two model ensembles. Page 5 in the paper shows a really clear positive trend. The more different the two models were in their prediction patterns, measured by that L2 distance we talked about.
Right, how far apart their signatures were?
Yes. The larger that distance, the better the resulting attack accuracy. So more diverse model pairs led to better reconstruction.
Okay, confirming that diversity is key.
And furthermore, Figure 6 shows that their farthest model sampling technique, FMS,
The smart selection method.
right, It generally did a better job at selecting effective models for the ensemble compared to just picking them randomly, especially when they were building larger ensembles, like selecting 4 models out of 8. So strategically selecting a diverse set is important.
That really drives home the power of combining these slightly different perspectives. It's not just about having more models, but having different kinds of models, in a sense.
Absolutely. And it's not just about having totally different models trained independently either. They did another fascinating
Oh,
experiment.
yeah. What was that?
They tried creating an ensemble
Yeah.
using different snapshots of the same model, just taken at various stages during its training process, like saving the model weights after 10 epochs, 20 epochs, 30 epochs, and so on.
Wow. Okay. So just different points in the learning journey of one model.
Exactly. Table 2 shows that even in this case, using more models from different training epochs led to improved attack accuracy.
No way.
Yes. And it also made the reconstructed images more similar to the original training data. They even measured this similarity using features extracted by a completely different image classifier trained on a different dataset, CI4100, just to show general image resemblance was improving.
That's incredible. So even if a company thinks they're safe because they only keep the final version of a model,
Right.
older versions or intermediate checkpoints they might have stored somewhere could still be exploited using this ensemble attack.
That's the implication. It's quite a sobering thought for model security practices.
Yeah, no kidding. Okay, so that covers the digits pretty thoroughly. What about the experiments with recognizing faces? That feels even more sensitive.
It definitely does. For that, they used models trained on different subsets of a large face dataset called VGG Face 2.
Okay.
And importantly, these different training subsets had some of the same individuals in them.
Ah, so like a realistic scenario where maybe someone's picture is in a data set for one application and also in a slightly different data set for another.
Exactly. A situation where an attacker might be specifically interested in identifying individuals who appear across multiple datasets. They used ResNet 34 models for the ensemble under attack,
Okay.
and a different architecture, a VGG16 model, for that independent evaluation, again, focusing just on those identities shared across the training subsets.
And did they see similar improvements with ensemble inversion when it came to faces? Better recognition, better pictures?
Yes, definitely. The results shown in Figure 7 and Table 3 clearly demonstrate that using an ensemble, in this case of 5 models, significantly improved both how accurately they could identify the faces and the visual quality of the reconstructed faces compared to attacking just a single model.
Visually better, too, so clearer faces.
Yes, noticeably clearer and more identifiable. Figure 8 also really emphasizes this improvement, especially in those tougher data-free settings. Even if the reconstructed images are still somewhat rough without auxiliary data, the ensemble approach yields much better results than attacking a single model.
Wow.
They also noted that by tweaking the balance between the different loss functions, LOH, LMR, may be the realism loss if auxiliary data was used.
Right, adjusting the knobs.
Yeah, they could achieve different trade-offs. For example, you could prioritize making the generated faces look more photorealistic, or you could focus more on just capturing the key distinguishable features that make a specific individual recognizable, even if the image isn't perfectly natural looking.
So the attacker has some control over whether they want a pretty picture or just the identifying information.
Potentially, yes. It highlights the flexibility of the attack, that class correspondence problem we mentioned earlier.
Matching ID 1 to subject 7.
Right. It's like trying to figure out that customer ID 123 in one company system is the same person as account number 456 in another system used by maybe a partner company. That's the kind of puzzle this attack methodology helps solve by looking at model behaviors.
Okay, so the overarching message here, it really seems to be that going after multiple related machine learning models at the same time, this ensemble inversion technique, is potentially a much more powerful way to uncover private training data than just hammering away at a single model in isolation.
That is absolutely the core finding, yes. By taking advantage of the natural variations, the diversity that exists even among models trained on the same or similar information.
Variations that just happen naturally during training.
Exactly. And by employing smart strategies like that farthest model sampling and those specialized loss functions, LOH and LMR, the quality and accuracy of the reconstructed training data can be significantly boosted.
And this has some pretty serious implications for privacy, doesn't it?
Yeah,
Especially, look, you mentioned, in areas like federated learning, where lots of different parties contribute data or model updates.
definitely.
Or really any situation where multiple versions or related models might exist. I'm thinking, imagine your anonymized health data being part of several different research models, maybe one for heart disease risk, one for diabetes predictors.
Right. Trained by different institutions, perhaps.
Exactly. Individually, they might seem relatively safe, properly anonymized, but this research suggests that by looking at them together as an ensemble, someone could potentially piece together much more about your specific health history than from any single model.
That's a bit unsettling. It is unsettling. The fact that an attacker might be able to construct a more complete, more detailed picture of sensitive training data just by targeting an ensemble of models raises significant concerns. The researchers themselves really highlight the urgent need now to develop new defense mechanisms. Defenses specifically designed to counter these ensemble inversion attacks, not just single model attacks.
Right, the defenses need to evolve too. So, what does this all mean for you listening in?
Well, just consider the sheer number of AI models that are becoming part of our daily lives and the enormous quantities of data they learn from.
It's growing constantly.
This deep dive into ensemble inversion really highlights just how intricate and how dynamic the risks to our privacy are becoming in this age of AI. It really makes you think about the security of the information that fuels these powerful technologies and, the ongoing sort of cat and mouse game between those trying to access private data and those working hard to protect it.
It's a continuous challenge. Absolutely. And it leaves you wondering what new vulnerabilities might emerge as we create and deploy even more complex, more interconnected AI systems in the future. It's definitely something to ponder.